Okay, so the challenge in greedy algorithms is understanding whether or not the algorithm gives you the optimal solution. So let's practice this, and we'll practice this on a variation of the knapsack problem, where greedy algorithms actually do give us the optimal solution. So first, let's think back about the knapsack problem, and let's understand why, on the variations of the knapsack we've looked at so far, a greedy algorithm isn't guaranteed to give us the optimal solution. So our first question is kind of this. Why in the 0-1 knapsack, where I can either take whole items or not take items, right? Those are my two options. Why in the 0-1 knapsack is the greedy algorithm not correct, right? Why is it not guaranteed to give me the optimal solution? So why is greedy bad in the 0-1 knapsack? So to reason about this, to try to understand why greedy fails, let's think back to our DP idea. Right, so the DP table that we drew, we spent a whole week thinking about this, said this, like let's think about putting our items down the rows of our DP table, and let's think about putting the value or the weights of the items, or I should say the capacities of potential knapsacks, or of conjectured knapsacks along the columns of our table here. And then we can kind of think about this in terms of a greedy algorithm in two ways. The first way is to start here in the lower right. So the question in our algorithm is what value belongs here, right? What is that f of n and w? And the thing we observed in the DP algorithm is that it either depends on what's here, or it depends on something that's over here. And so if you're trying to understand what's the best thing you can do at the end of the algorithm, or what's the best way to solve the overall problem, the only way to be sure that you've solved the overall problem and that you've gotten the right answer, at least kind of informally, the only way to do this is to understand what is the optimal here and what is the optimal here. So to solve the whole problem, you need to have at least two other solutions complete, right, and correct. So need correct solutions to two subproblems. Okay, and that seems to be fundamental for the knapsack problem, at least the way it's set up right here. That there's no way to certify that your final answer is correct unless you have certificates that the two relevant subproblems both have correct answers, right? And the only way to get those is to solve two more each, and then two more each, and two more each, until we have a whole bunch of stars all throughout our table. Okay, so it's not clear how knowing only one of those would get you the answer to the final the overall problem. So why do we care about how is this relevant to greedy? Well, think about what happens in greedy. A greedy algorithm always starts here. So greedy starts here. Starts up here. And what the greedy algorithm does is it says, I'm going to look at the stuff I could do, and I'm going to make one choice, and then I'm never going to revise that choice. Okay, so what greedy does is basically it says, I'm going to take one unique step forward and then never look back. And then when I get there, I'm going to take one unique step forward, and then I'm never going to look back. And then when I get there, I'm going to take one unique step forward, and I'm going to keep doing that until I can't take any steps anymore, and then I'm going to return a solution. And so what does that do in terms of something like this, a picture kind of like this? Well, that gives us one path, right? A greedy algorithm can only have one path. It never branches. Whereas the DP algorithm branches by construction. The only way the DP algorithm can ever certify that its answers are correct is by considering the difference between two different already solved problems. And to do that, it has to have branched at some point in the past. So a greedy algorithm only goes kind of along one path through the set of feasible solutions. Whereas the DP algorithm, by construction, it spreads out. It spreads out through the paths. And so the greedy algorithm could get you the right answer, if it happened that this path landed in the correct one of these two boxes. But, fundamentally, you don't know for sure that it's going to land in the correct one of those boxes, because you don't know which box is the correct box until you've explored them both completely. So the reason, at least at a high level, that the greedy algorithm fails in the 0-1 knapsack problem is that it can only choose one path through the space of feasible solutions, whereas to understand whether or not a solution is optimal, you have to have explored more than one path. So you can basically think of it like this. Greedy fails because it only explores one path. One path. And DP explores them all. Explores all the relevant paths. And so just by the way, this is one way you can kind of connect a greedy algorithm to a DP algorithm. And you can notice that a greedy algorithm is a DP algorithm where we have a guarantee that there's only one path, right? That there's only one relevant path to the final solution. Okay, that's one way you can kind of conceptualize the relationship between these two. Okay, so let's think about a variation of the knapsack problem, just a subtle variation, where a greedy algorithm is optimal. Okay, and this is called the fractional knapsack problem, as opposed to the 0-1 knapsack problem. So fractional knapsack. And so think about the original kind of motivation of the knapsack problem, and that's that there's a thief that breaks into a mansion and has like a limited capacity in his bag to take stuff away. And he's in a mansion, so all he can do is take like whole items. If he cuts a TV in half, it's not a TV anymore. So he's only taking whole items, and he has a limited capacity. And so there's this kind of Tetris packing problem that's challenging. So the fractional knapsack problem is more like the burglar breaks into a warehouse full of bulk goods, and there's like a bag of gold dust here, and a super sack of flour over there, and a whole bunch of oats or something like that. And he gets to decide how much of each of the substances or each of the items to take. So fractional knapsack, you can think of this in terms of, rather than items that you're taking away, you can think of this in terms of bulk goods or divisible goods, right? So I'll say bulk or divisible goods. Okay, and the distinction from the 0-1 knapsack, right? So we can write 0-1 knapsack, whole items. Whereas the fractional knapsack, you can take fractional items. Hence the name fractional. The fractional knapsack is also like the knapsack in a world where if you cut a TV in half, it's a TV that's half as valuable or something like that. Okay, so let's go back to the same example we did before, but let's think of this now in terms of a fractional knapsack problem. So we'll have our overall capacity W be 10, just like before. We'll have 4 items now, 4 like substances or bulk goods. And so I will arrange the items in a table like this. So item 1 has a value, and so now this is the value of the full amount of the item. Okay, so if the thief took all of item 1, then what he would get is something that's worth $42. Okay, and now the total weight of this item, I'm going to VI WI, the total weight of this item is 7. So think of it like there's 7 pounds of this stuff, and if the thief took all of it, he would get $42. Right, so all 7 pounds together is $42. And so we can also think of like the per pound value of this stuff. So let's think of the unit price of this stuff as the VI divided by WI. Sometimes I'll erroneously call this the density, but it's the per unit price of this stuff, the per unit of weight price. And so you can see this has a per unit price of 6. Okay. So if he takes 1 pound of this, it's worth $6. If he takes all 7 pounds, it's worth $42. So bringing half of it gets him half the total value. So item 2, and these values and weights are the same as from the previous problem, but now I'm also going to include this third column of the value per weight. All right, so the second item is $12. $12 for all of it. There's 3 pounds of it, and its value per weight is 4. So 12 divided by 3 is 4. So notice these 6 and 4 numbers aren't arbitrary. This is the value divided by the weight. Okay. Item 3 I think is the good one. Yeah, so item 3 is $40 altogether. There's only 4 pounds of it, but because $40, it's 4 pounds for $40. That's $10 per pound. And then item 4 is $25 total. 5 pounds altogether, and the value per weight is 5. Okay, so here's our fractional knapsack problem. What makes this a fractional knapsack problem? I said it was 1. Okay, so it's specified exactly the same way as an ordinary knapsack problem, but now I'm saying, instead of taking only whole items, you get to take fractions of items. So if you want to just take all of item 2, all of item 3, and then some of item 1, you're welcome to do that. That's completely fair. And so now let's think about what a solution might look like. So in the next video, we'll set this up in a fundamental mathematical way, and then we'll think about how to solve this.